All right, today we are talking about lesson 6.4 in our Algebra 2, and we are talking about factoring polynomials, but we are going to bring back the remainder theorem from our division and talk about binomial factors to start. So, the remainder theorem states if a polynomial is divided by x minus a, and I want to remind you that that's a binomial, the remainder is the value of the function at a. So if x minus a is a factor of p of x, our dividend, then p of a equals 0. All right, so let's talk about that in real terms that's a little bit more understandable. Basically, we want to know that if a polynomial divides evenly, then the divisor is said to be a binomial factor. So if a polynomial divides evenly by this x minus a, this binomial factor, then the divisor is said to be a binomial factor. Basically, if there are no remainders, that should make it easier. If there are no remainders, then we've divided evenly. All right, so for example 1, I could jump in and factor this and see if this is a factor, but we're just going to sort of do another refresh of our longhand division. When I go ahead and do longhand division, I'm going to make sure I go in standard form if I need placeholders. So power of 2, power of 1, power of 0. So x squared plus 2x minus 3, and we're dividing by x minus 3. So just to recap a longhand division, how do I make this first term x into an x squared? What do I multiply by? I multiply by x. I bring it in by distributing, and that would give me an x squared minus 3x. I always subtract here. We want to make sure we change out our signs. And then our first term should cancel, and that leaves us a 5x, and drop down the next term of minus 3. And then we start again. How do I make that x look like a 5x? I multiply by positive 5. So I take my 5 times x, gives me 5x, and I take my 5 times negative 3, which gives me a negative 15. I come through and I subtract. I like to change the color so I can show that that's a sign change. This cancels out, and it leaves me a remainder of 12. Okay, so a couple things. How do I write my remainder? I have my answer, x plus 5, plus 12 pieces of the divisor, x minus 3. So that is my answer to my division problem, but because I have a remainder, it did not divide evenly, so x minus 3 is not a binomial factor of p of x. That's what I know. Because I have a remainder, this binomial is not a factor of my quadratic trinomial. All right, so we're going to try that again, and we are going to do longhand division here. When I go to set up this problem, I notice that I am missing something. I have a 2x to the 4th, I have an 8x to the 3rd, but I don't have a 0x squared, so I want to put a placeholder there. Plus 2x to the 1st plus 8. So we need a placeholder of 0x squared. That's going to help us line up our answer in division. We are dividing by x plus 4, and so we start. How do I make x turn into a 2x to the 4th? I multiply by 2x to the 3rd, and again, I distribute that. So 2x to the 4th, and then I get a positive 8x to the 3rd, and I want to come through and I want to subtract. Now, we need to be careful here with this one, because what happened was this canceled out and that canceled out. So I really get 0x to the third, and when I drop down my next term, I get a 0x squared. So if I wanted to play out all the pieces, I would start again. How do I make x look like a 0x to the third? And I'd have 0x squared. And I would go through the motions. In the end, this is still going to zero out. So I really can come down and drop my next two terms. For some people, they need to see it go through, so they'd put the 0 here, they'd fill in the zeros, bring the next term, and start again. These would all zero out. You can go through that, but I'm going to jump from x to 2x by saying plus 2 and just plus 2. All right, I've already got the x. All right, so we would take our 2 times x and get 2x, and our 2 times 4 and get plus 8. And when I go to subtract, I get a remainder of 0. And because I have a remainder of 0, this divided evenly, which means that x plus 4 is a binomial factor. X minus 4 is a binomial factor of p of x. So in these problems, the answer was not actually the 2x to the third plus 2. The answer was it is or is not a binomial factor. Okay, so if it divides evenly, it's a binomial factor. If there's a remainder, it's not a binomial factor. All right, our next concept that we're working on is factoring by grouping, which is a review for us. So we are factoring polynomials. We had covered this in chapter 5 when we went over quadratics. So one of the things when you do factoring by grouping, your first rule is always to look for a GCF. If you don't do that at the beginning, you have to do it at the end, and we'd rather do it at the beginning, make it easier. So I do not have a GCF here. When I factor by grouping, I'm going to group the first two. We like to squeeze that minus sign in and put our own plus sign. When I factor by grouping, it's always the first two plus the second two, and then we work with our negative sign. We're doing two simple GCF problems. The first set, we have an x squared in common. What's left over is x plus 3. I'm going to put my plus sign down here. And in my next set, I'm going to take out not just a 4, but a negative 4. And that leaves me x plus 3. So by taking out the negative, we've changed the signs. And now we see we have two terms. Here's 1 and here is 1. A little more abstract. What they have in common is x plus 3. We're pulling that as the common factor. It is not squared. That comes out front. What's left over is x squared plus a negative or minus 4. Okay, so we looked and we took out the GCF of x plus 3 and we brought in the leftover. If I take the x squared times x plus 3, I get back to here. I take the negative 4 times x plus 3, I get back to here. Now there's one more thing I always want to look at. This is factored completely, but I have an x squared here. And this brings us back to a difference of squares. I have a difference, subtraction of two square terms. The middle term is 0. So the x plus 3 is going to stay, but this is going to break down to x plus 2 and x minus 2. The x times x is our x squared. 2 times negative 2 is your negative 4. And what we want to double check is that negative 2x and positive 2x cancel out to 0x. So we have seen difference of squares and worked with them. We've also used the concept of difference of squares when we rationalize denominators of imaginary numbers because we use the complex conjugate. So this is my final answer. All right, so we start our next one. We look for a GCF. I don't have one. So I'm going to group it, squeeze that minus sign, and put in your own plus sign. That negative sign sticks with the 25. It does not distribute. Look at your first set, factor out an x squared. What's left is x minus 1. Look at your next set. I want to factor out a negative 25. I always want to pull the negative to make it match. So now I have a positive x, but a negative 1. And it's really important to have that 1 there, so when I reverse the distribution, I get my 2 terms back. Okay, if you can take a minute and look at this, a little bit more abstract, these 2 terms have an x minus 1 in common. So once I take that out, I am left with x squared minus 25. And so I see the x minus 1 is fine, but that x squared should tip me off. That should make me want to look and say, can I keep factoring? And I see here that, again, I have another difference of squares. So x minus 1, and then here we have x plus 5, x minus 5. And that is my final factored form. Now remember, the order of your factors does not matter because multiplication is commutative. All right, so the first thing I wanted to do was try to take out a GCF, but there was no GCF because this does not have a 2, that does not have an x. So I'm going to come in and I'm going to group this. This one has a plus sign, so I'm going to leave it in the middle. I want to make sure it doesn't show multiplication. GCF in the first term is x squared. What's left is 2x plus 1. Again, that 1 is very important, so I get my numbers back. Okay, plus, here I can take out a 4. I want to take out the GCF. What's left is, again, 2x plus 1. So what do these two have in common? They both have the 2x plus 1 in common. And then what's left over is x squared plus 4. So I'm looking at this, and my tip-off should be that there is an x squared there. But I want you to realize that this does not factor. It has to be a difference of squares, and that's a common mistake, is that we just jump in, well, this had an x squared and that had an x squared and this looks just the same. It does not. So this actually is my final answer. It does not factor further, but let me show you why. If I have x squared plus 4, there are no factors of positive 4 that add up to 0. That's why it has to be a difference of squares. So try as I might, plus 2, well, I get 2x and 2x, that adds up to 4x. I change them to minus 2's, negative 2x, that adds up to negative 4x. So then I get the idea, well, I'll make 1 plus 1 minus. Okay, well, I have got the 2x and the negative 2x to cancel to 0, but do I now have a positive 4? No, my last term is a negative 4. So this does not factor further. So that is my final answer. So this was part of 6.4 where we talked about binomial factors. If we have a remainder, it is not a binomial factor. If it divides evenly with no remainder, it is a binomial factor. And a nice review of factoring by grouping. Always take out your GCF. Break it into 2 small factoring problems and then looking at the big picture.